Thank you for joining us to this first webinar of June of SN Applied Sciences. My name is Elisa Collado Fregoso, and I'm the managing editor of the Physics, Material Science, and Interdisciplinary sections of SN Applied Sciences. So we're very happy and very honored to have our speaker, our speaker of the day, Professor Daniel Randonea, who's joining us from the Universidad de Valencia. And he's gonna talk about high pressure characterization of indium oxides for water splitting applications. So we are very happy that he is with us. And I'm just gonna tell you a little bit about what he's been working on. Professor Randonea is a full professor at the Applied Physics Department of the Universidad de Valencia in Spain. He received his master's degree in physics at the Universidad de Buenos Aires in Argentina, and his PhD in physics at Universidad de Valencia in 1998, after working as a postdoc researcher in the Max Planck Institute in Mainz in Germany. He joined the Geophysical Laboratory in the US, and he became Ramon and Cajal Fellow at the Universidad de Valencia. He was then appointed full professor and won the Alvin van Valkenburg Award, among others. So we're very happy to have Professor Randonea with us. And without further ado, I would like to just pass to you, Daniel, and the floor is yours. So I'm gonna stop sharing.
I will talk today on the high pressure studies we have done in indium oxides. I will then explain which I refer with indium oxides, which is not the real indium oxides. And these are studies we perform in materials that has been postulated to be used for water splitting applications. This is a research we have done at the University of Valencia. Our team is part of the EFIMAT consortium, and it's also a part of the Malta Consolidator team, which is a high pressure expansion network. My research has been supported by the Spanish government and by our local government. So I have organized the presentation in this way. First, I will comment on what are the oxides we have been working in, then why are these compounds of interest, then I will say why we need to study them under high pressure, and for those who are not experts in high pressure, I will explain how we reach the high pressure. Then I will focus on phase transitions induced by pressure. I will correlate structural changes induced by pressure with electronical and vibrational properties. Then I will comment on one of the most important issues we have discovered, which is a pressure-driven induced band gap collapse. And finally, I will present my conclusions. So when I refer to indium oxides, I'm referring to ternary oxides, not to indium oxide itself. So these are always compounds with this composition, indium, another cation, and then O4, where X is any atom which could be a pentavalent cation. Basically, we will have two families. One of them that include indium niobate and indium tantalate are monoclinic compounds. In these compounds, indium and the other cation are octahedrally coordinated. And in the second group, which include indium vanadate and indium phosphate, I will comment most in indium vanadate today, and then I will say why I prefer to talk on indium vanadate. In this one, the structure is more symmetric, is orthorhombic, has indium still in octahedral coordination, but vanadium is tetrahedrically coordinated. So this is the main difference. We have here a group which has high symmetry and a group which has a lower symmetry. So why we are interested in this compound, or why people is interested in those compounds? People doing applied physics are interested in them for many reasons. One is that indium niobate, indium tantalate, and in particular indium vanadate has been postulated and tested by different people for uses related to clean hydrogen production via photocatalytic water splitting. They also postulate to use this compound to degrade pollutants by means of photocatalytic reactions. On the other hand, we and other people have shown that if you dope this with rare earth, they are ideal compounds to be used in light emitting diodes, in particular in white LEDs. They have been also postulated for many other applications, which include electrolytes for lithium-ion batteries, active material for gas sensor, photovoltaic cells, and many other more. The list is quite long. In addition to that, we are also interested, or we start to be interested in these compounds before knowing their application because of reasons related to our fundamental research. So the family of oxides with this composition, AX04, all the ternaries oxide with this composition are very interesting for crystal chemistry, for geophysics, for many reasons. One of them is because of the compositional diversity and structural simplicity. They play a key role in developing comparative crystal chemistry. So it's important to build a systematic understanding what happened with all this family of these compounds and the high pressure. So understanding them will make a crucial contribution to the understanding of the high pressure behavior of many other oxides. So because of this, we and many other groups have been studying multiple of these oxides. For instance, the zircon family, the scheelite family, the monazite family, the wolframite family, anhydrite, barite, and many others. But till 5 years ago, nobody has paid attention to indium vanadate, indium niobate, and indium tantalate, which don't fit within any of these families. So in spite of that, there is an important thing related to basic research, which is the fact that there is a big controversy in the literature regarding the fundamental properties of these materials, in particular regarding the band gap. As I will show later, you can find for a given compound, for instance, indium vanadite, different reports of the band gap energy, which can go from nearly 2 to 4 point something EV, which is a huge difference. And that's not possible. So we need to do some accurate determination of the band gap energy, which will be crucial to know if this material can be applied or not in different technological applications. So then why we study them under compression? So the main thing is because under compression, we reduce the bond distance, modifying the interatomic forces. This usually leads to important changes in the material properties. That way, high pressure studies are very helpful for understanding the physical properties of the solid state and also for testing the understanding we have of the properties at ambient pressure. The models that we have developed for ambient pressure, if they are correct, they should also hold for high pressure conditions. Another interesting thing is that high pressure induced phase transitions. In some cases, it could be metastable, and we can recover the high pressure phase at ambient conditions and induce important changes in the physical properties in the materials of interest. One of the properties that will be strongly affected will be the band gap. Then, because of the open crystal structure of many of these ternary indium oxides, phase transitions were expected to happen at relative low pressure. Relative low pressure, I mean below 10 GPa. So 10 GPa is 100,000 atmospheres, but for those working in high pressure research, that's a very low pressure. The importance that the transition happen at these very low pressures is that they favor the possibility to study these compounds under nearly hydrostatic conditions. This means that all the changes we are inducing in the material, we can assume they are just induced by pressure and not by other stresses like deviatoric stresses. So then how we study them? So those who are expert in high pressure, they know that we have used, or everybody used for doing these studies, which is the so-called diamond anvil cell, which basically for those not familiar with it, it's just two diamonds which have the culet facing one to each other. In the middle, we put a metallic gasket where we drill a little hole, micron-sized hole, where we will put our sample. Could be a crystal or a powder. A pressure standard, in this case is a ruby ball, which will determine the pressure, and the pressure media that will guarantee the quasi-hydrostatic conditions. By this way, we will modify the properties of the material, as is shown here, and in order how we modify these, the properties, we need to make some characterizations. Since diamonds are transparent to X-ray or to visible light, we can go to synchrotron facilities in order to have a very bright X-ray sources and do powder X-ray diffraction, determining the changes on the crystal structure. Since the diamonds are transparent, we can use laser to measure Raman spectroscopy and then determining what happened in the vibrational properties of the materials. We can do also optical absorption to characterize what happened with the electronic properties and mainly with the band gap structure. We can do resistivity, not always in diamond cell because of the tiny of the pressure cavity, but using other kind of cells that I will show later, which also helps to characterize electric properties. We can measure luminescence and many other properties. So the amount of experiment we can do is large. And in addition, we always cooperate with colleagues doing DFT calculation, which will be used for the interpretation of our experiments. They will contribute for the understanding of our experimental results. Okay, so which samples we have used? The sample we have used has been prepared for some of our collaborators. They synthesize powders by the solid state reaction. We check for the purity of this powder. They were high purity. We check it by means of EDAX measurements. We check the crystal structure is the one expected, and we did it by powder X-ray measurement. All these measurements were done at ambient conditions before loading the samples in the diamond anvil cell. So as you can see here, and as I showed before, two of these compounds, the indium niobate and the indium tantalate, will crystallize in this monoclinic structure. In this structure, we have change of zigzag change of indium octahedra and also zigzag change of niobium or tantalum octahedra. And in this one, we have linear change, which is more symmetric and is orthorhombic. We have linear change of indium octahedra, which are connected by corner shear in vanadium tetrahedra. And this will be fundamental for the behavior of the material under high pressure. Let me start talking about indium vanadate first. So indium vanadate, we had performed X-ray diffraction experiments. These are results from the X-ray diffraction experiment we did at the ALBA synchrotron in Barcelona. You can see here all the peaks. Most of them can be identified with the orthorhombic structure, which is this structure, the one we expected. We only have two peaks, which is copper, which is our high pressure calibrant, and another broad peak, which is a reflection from the gasket we use to contain the sample. But in addition to these two and this other peak, everything can be well explained by the well-known orthorhombic extractor. This happened again when we start increasing pressure at 5.3 GPa. Still, we have only the orthorhombic low pressure extractor. However, when we increase further the pressure, we reach 6.2 GPa, and you start seeing here some new peaks, which I depict by asterisks, like this one, this other, and several more, which are indication of the onset of the phase transition. As we keep increasing pressure, you can see that the peaks from the low pressure phase start losing intensity. This is clear here. And these peaks start growing in intensity. And if you further increase the pressure, you lose off the peak of the low pressure phase and you get all new peaks, which correspond to the high pressure phase. More things we can see here is that you can see here, you can compare these three peaks, which correspond to 020, 002, and 200, which move differently under pressure. That indicate that the compound has a highly anisotropic behavior. Other things you can see is that when we compress from 8.2 to 22.4, there is no further phase transition. So we have only two phases, which I call phase 3 and phase 5, because the ambient pressure phase is already known as phase 3 in the literature. There's another phase which is called phase 4, which is obtained under high pressure, but also high temperature, which is different than the new phase we discovered. So the new phase, we call it S5. These are readable refinements from the low pressure phase, showing that the structure is correct. And after working with the Xray pattern of the high pressure phase, we have found that the high pressure phase is a monoclinic structure, not only a monoclinic structure, but with the same space group that indium niobate and indium tantalate. So pressure is going from the high symmetry, low pressure phase, we will move to a low symmetry, high pressure phase. And in addition, the formula units in the unit cell is divided by 2. So not only that, if we assume the same structural model that for indium niobate, so we use this structure for the high, okay, not this structure, something isostructural to it for the high pressure phase, we can very well explain the high pressure phase of indium vanadate. So it looks like indium vanadate under compression is taking the structure of indium niobate and indium tantalate. And this is not surprising because niobium and tantalum are very large cations in comparison with vanadium. So substituting vanadium by any of them is equivalent to applied pressure in the compounds. So more things. Our colleague has done ab initio calculation. This is the enthalpy, the free energy versus pressure. And you can see that at low pressure, the most stable structure is this orthorhombic one, which is expected one. But as we increase pressure, the monoclinic structure, which is this one, see, is becoming the more stable. It's what is so-called wolframite here. At pressure beyond the limit of our studies, our colleague predict 2 additional phase transition, but I will not comment on that here. This is beyond the scope of this talk. Another interesting thing is that we can go from the low pressure phase to the high pressure phase just by using group-subgroup relationships. We can transform this orthorhombic structure into a C2C structure, which can be easily transformed into the P2C structure. So these group-subgroup relations give an idea of a possible the possible mechanisms driving the phase transition. From the experiments, we obtained information on what happened with the unit cell parameters. You can see here clearly that this axis is much more compressible than the other two. So compression is anisotropic, as I commented before. Is also anisotropic for the high pressure phase. However, we see 2 important things. One, The bulk modulus of the low pressure phase is 70 GPa, which makes indium vanadate the most compressible vanadate studied until now. This is reasonable because this crystal structure of indium vanadate is very open. When we have the phase transition, we have a large volume collapse. The volume decrease a lot, like at 20%. The high pressure phase became much more dense, and therefore is much less compressible, being the bulk modulus 170 GPa. Here you have results from Raman experiments. In the Raman experiments, again, we can identify this Raman spectra with the low pressure phase. The low pressure phase has 18 Raman active modes, but then when we keep going beyond 6 GPa, we start seeing changes which correspond to the change of the Raman spectrum from that of the orthorhombic structure to that of the monoclinic structure. You can see probably more clearly here the change where we plot the pressure dependence of Raman modes. Here you have the low pressure phase, and here you have the high pressure phase. And the change is very noticeable in the frequencies. In special, you can see here these modes are related to internal vibration of the vanadate unit. And something I didn't comment yet is that when we have the phase transition, there is an increase in the coordination of vanadium from 4 to 6. That make the vanadium oxygen distance to elongate a bit in order to accommodate 6 oxygens around vanadium, and therefore the stretching modes will lower their energy. As you can see here, the highest frequency modes is around 900, and in the new phase is clearly below 900. If we go to the other compounds, which are crystallized in the monoclinic structure already at low pressure, we have seen by Xray diffraction that they can be explained by the low pressure phase until 9.1 GPa. But at 13.1, you will start to see changes. This red Xray pattern corresponds to a relation we have attributed to a phase coexistence between the low and the high pressure phase. And then the blue ones correspond to the high pressure phase. Under decompression, we fully recover the ambient pressure Xray pattern, so the transition is reversible. We have been working with this pattern, and what have been able to identify with the help of the calculation the high pressure phase as another monoclinic structure described by the same space group, but different than the previous one. And in this one, we have both cations coordinated with 8 oxygens instead of with 6 oxygens. And this will have also important consequences. You can see here the calculation where they predict both in the enthalpy and in the total energy there is a phase transition there and there. You can see here Rydberg refinement with the low pressure phase and the high pressure phase. And so the transition go from the same spectral group P2C to P2C, so it's isosymmetric. Then according to the theory of phase transition, the transition should be necessarily first order. This is the first order transition as in indium vanadate. We confirm its first order here by this volume change. Again, compression is highly anisotropic, and you can see that the low pressure phase has a bulk modulus of 180 GPa, which is comparable to the one of indium vanadate at the same phase. So remember, this high pressure phase is isostructural to, with the bulk modulus of 170 GPa, is isostructural to this phase, which has a bulk modulus, to this one, which has a bulk modulus of 180. After the transition, there is an increase, but the increase in the bulk modulus that is not so important as in the other compounds. Here again, you have evidence of Raman experiments showing the onset of the phase transition at 13.4, and then having the pure phase 2 at 19 GPa. And again, the Raman spectra, as expected, is reversible, as happened in the Xray diffraction patterns. Here again, you can see the change, and you can see the decrease of the frequency of the internal stretched bone mode related to internal vibration of the vanadate units. These are results in indium niobates. The results in indium niobates are very comparable to those in indium tantalate. The only thing is that the transition only completely happened at 20.7 GPa, which is close to the highest pressure we reach in the experiment. But again, the transitions are reversible. 1.2 GPa and 0.1 after pressure release gives the same instructor. Again, the low pressure phase of indium niobate is isostructural to the low pressure phase of indium tantalate, and the high pressure phase are also isostructural with the two cations coordinated by 8 oxygens. Calculation also predict the same phase transition. You see here the enthalpy is crossing around 70 GPa. And again, we have a highly non-isotropic behavior. As in indium tantalate, the bulk module of the low pressure phase is close to 180, and the one in the high pressure phase is a little bit about 220. So all these changes, in particular the drastic changes at this phase transition, should have important consequences in the electronic properties. I will show now here, this is another slide to show that Raman experiment also confirmed the same phase transition as an indium tantalate, but I would like to focus in the electronic properties. This is just another slide before commenting on the electronic properties. These are luminescence experiments in a compound which has been doped with europium. You put europium will substitute indium. So it's X coordinated in the low pressure phase, it's X coordinated in the low pressure, in the high pressure phase. So the crystal field of europium will considerably change. And you can see here in the luminescence signal how it changed beyond 12.2 GPa. Indeed, the luminescence experiments show we have the pure low pressure phase till close to 13 GPa. We have a coexistent region, and then we have about 18 GPa, the high pressure phase, which remains stable up to 35 GPa. Okay, so now let me focus the remaining of this talk on the electronic properties, which was the main topic of the article we published some time ago in SN Applied Sciences, and which has gotten a lot of attention and a lot of citations. Here we focus on the band gap. The main reason of focusing on the band gap was that I mentioned at the beginning, there were significant discrepancies in the literature on the energy of the band gap. For instance, in indium vanadate, there were results going from 1.8 to 4.8 EV, which is nearly 3 times the lowest value. And there was a debate about whether the transition was indirect or direct. So we believe that, okay, we have proved that the band gap is in the high range of values, not 4.8, but a little bit below it. And indeed, I will show that the energy assigned to the band gap in the past, indeed, is not the band gap, but is absorption of light related with defects present in the sample. So this was the model before we did our study of the band gap. It was assumed that the bottom of the conduction band was mainly due to the electron of the transition metals, and this was given an explanation to the fact that the expected band gaps were close to 2 in the case of the vanadate, at 2.5 in the case of the other compounds. Most of these results come from these experiments, which were absorption or, in many cases, diffuse reflectance, and people was assigning this to the band gap in these two compounds, which is not correct, and we're assigning this to the band gap in this compound, which is not correct. The band gap is this one, which you will see is crossing close to 3.5. And this is just absorption. It's an Urbach tail related to the absorption of defects. This is important. It's not for your applications. If the band gap is 2.3 or 3.6, it's very different. So we have accurately determined it. So we have done optical absorption experiments. This one is and you can see here better, is the one at 1 bar pressure. We have here a very sharp absorption, which indicated a direct band gap. And you have here an absorption tail, which is what I told you, the Urbach tail. Indeed, if you use this model, which is a direct band gap plus the Urbach tail, you can explain very well our absorption. This is done here, where we compare this black solid line with this red dashed line. The red dashed line is the model. So this way we have determined the band gap energy as a function of pressure. Calculation confirmed that the band gap is high. Indeed, they predict DFT predict a 4 EV. And you can see here that the bottom of the balance, the top of the valence band is mainly dominated by p orbital of oxygens, with a contribution of orbitals from indium, but the bottom of the conduction band is dominated mainly by 3D vanadium atoms. This will explain why we have this. If we have an increase of the repulsion between bonding and anti-bonding state of the vanadates with pressure, because the bond distance is decreased, you expect an increase of the band gap, as we have seen in our experiments. So you can see here, we have a blue shift of the band gap with pressure, which you can also see here. So then we clearly rule out these measurements indicating this low band gap, and we have shown that this is not the band gap, but this is the band gap, which is in agreement with our results. Indeed, we have done also reflectant experiment, which showed a band gap, 2 band gaps, one around 3.6 or another a little bit above 4. And this is photoemission experiments also done by us, which gives very similar energies for the band gap. So there is no doubt this compound has a band gap of 3.6 electron volts. If we keep increasing pressure, we observe a huge collapse of the band gap. You can see here, these values were around 3.6, and these are below 2.4. So we have a decrease of 1.5 EV. And the sampling did change from transparent to orange. This is clearly a consequence of the restructuration of the crystal structure. The calculation predicts this band gap to be around 1.8, which is a reasonable comparison to the 2.1 value of the experiment. And we have 2 band gaps, one direct and one indirect, very close in energy. As when we have this phase transition, there is a very important increase of hybridization between vanadium and oxygen states, and this is what produced the collapse of the band gap. If you go to indium niobate, we have seen similar results. You can see here. Again, we have here, you see, this is oxygen dominate, and I have niobate dominating the states in the conduction band. This is indirect, and this is important fact. We have 2 band gaps, 2 indirect band gaps, which are at ambient pressure. This one is the absolute minimum, but as we start increasing pressure around 3 GPa, this one becomes the absolute one. And this is what you can see here. There is a band gap crossover. Here we have one minimum dominating, and we have the other minimum dominating. But again, in spite of this band crossing, there is a blue shift of the band gap with pressure. If you go to the indium tantalate, I'm sorry. First, I will go to the high pressure phase. The high pressure phase is a direct band gap material. And again, we observe a collapse of the band gap due to the change of the coordination of the niobium, which go from values around 4 eV to values around 2.8 eV. It's not as big as in indium vanadate, but it's 1.2 eV. If you go to the other compound, we observe the same. Indium tantalate, it has 2 indirect band gaps. It blue shift under compression. The band gap is again, it's large. And you see 3.8 eV at ambient conditions. It increases with pressure. There is a crossover between the two minima of the conduction band, and then the slope change. And then when you have the phase transition, once again, we have the collapse. In this case, 1.3 eV, the high pressure phase is direct band gap. And in the high pressure phase, we have a small rest shift of the band gap with pressure. And everything is consistent with the results we got from DFT calculations. Okay. In addition to that, let me summarize. We have found by Raman and Xray diffraction one phase transition in each of the compounds, and in each of them, the phase transition is inducing a coordination change either in vanadium, niobium, or tantalum. This change will produce a collapse of the band gap in the 3 compounds. This also should produce change in the electrical properties, and we have done it here in resistivity measurements. Unfortunately, for this measurement, we have not used diamond anvil cells. We have used a large volume press we have in our laboratory. This is a kind of setup we use for the experiments. This is not the sample. This is another sample for a different experiment. I think this was cadmium telluride. But you make 4 contacts in the Van der Pol configuration. You put against, like in the diamond anvil cell, one anvil facing the other, and you apply force to increase the pressure. Conditions here are not hydrostatic, so the transitions may happen at lower pressure. In the case of indium vanadate, you see the transition here in this discontinuity and the resistivity, which happens around 2 GPa, not around 5. But this is because the conditions were not hydrostatic. And we observe the phase transition in indium niobate, which is also expected around 13 GPa. And in indium tantalate, which is expected even at higher pressure, is not seen in these experiments. We only see this gradual behavior of the resistivity with no discontinuity on it. The decrease here is not only due to the decrease of the band gap, but also because under pressure we induce defects by creating oxygen vacancies, which could behave as donor state, and that way the resistivity is decreasing because the free electron concentration increase with pressure. Okay, so these results have also implicances in other compounds. If we go to chromium vanadate is a material isostructural to indium vanadate. Again, you see at ambient pressure, chromium vanadate crystallizes in phase 3, the same phase that crystallized indium vanadate, which is orthorhombic. And we have seen by Xray diffraction, so this is a the refinement of the low pressure phase, that under high pressure, it goes to the same pressure phase. So clearly there is a systematic of many compounds crystallizing in this orthorhombic structure under compression at relative low pressure, going to a lower symmetry monoclinic structure, which is a wolframite structure. You can see here at 3.5, you have the start of the transition. You have here the 2 phases coexistence, and you have here the high pressure phase. So, and you have here results from calculations supporting the same transition. With the transition predicted at 3, if you take a look to the enthalpy, the transition is predicted at 3 GPa, and we have seen the onset of the transition at 3.5 GPa. Again, we have done Raman experiment. The Raman experiment showed the same phase transition, and we have done Also optical absorption experiments as in the indium vanadate, and we have observed exactly the same behavior. The band gap is slightly increased with pressure in the low pressure phase because of the repulsion between bonding and anti-bonding states. And then when the phase transition happens and there is a change of coordination and increase of the coordination, there is a collapse of the band gap. You can see it here, and you see here the change of resistivity. So you see here, you see this collapse, you see this collapse, and you go back to indium vanadate, and you can see the same collapse in the band gap. It's here, yes, and you go to the resistivity, and you also see the jump on the resistivity. So this happened in the two compounds. But not only that, not only we found this happened in chromium vanadates. More recently, this is a going on research. We have studied iron vanadate, which at low pressure is similar to chromium vanadate and indium vanadate. And these compounds, we have seen that it undergoes two phase transition, but the second high pressure phase, it's also the same high pressure phase, the same Wolframite phase that we had been observed in chromium vanadate and indium vanadate. So most of these compounds crystallize in the same structure. All of them have a common systematic going to these low symmetry monoclinic structures. And you can see here on the band gap that you have again band gap collapses with the transition. In this one, it has already a band gap of 2.2 eV at low pressure. And so the band gap becomes much more smaller than the other compounds under high pressure. So just to conclude, I have reviewed today recent high pressure studies we have done on the properties of indium vanadate, indium niobate, and indium tantalate. I had present evidence of the occurrence of pressure-induced phase transition, which has been discussed in detail. We have identified the crystal structure of the high pressure phase in all the studied compounds. We have discovered new phases. Indeed, the crystal structure of the new phases has been uploaded to the and validated at the ICSD. The high pressure structure of indium vanadate has vanadium 6 coordinated. The one of indium niobate has an indium tantalate has niobium and tantalum 8 coordinated. The transition caused important changes in Raman spectrum, in particular a jump in the frequency of the high pressure modes, which are the modes, internal modes of the vanadate, niobate, or tantalate units. These change of frequencies are related to the coordination increase, and we have accurately characterized the optical properties. I think we have solved all discrepancies available on the literature about the value of the band gap at ambient pressure, but we have also characterized it under high pressure. I discussed the influence of pressure on the band gap energy and established relation or correlations between the changes in the crystal structure, in particular in the coordination of atoms, with the changes in the collapse of the band gap, in particular the collapse of the band gap. I report resistivity results, and they corroborate the results from the optical absorption studies. And we had developed a systematic understanding of the behavior of the three indium ternary oxides we have studied under high pressure. Within our results, in particular, the determination of the value of the band gap can have an implication in technological applications, and the result of the high pressure study have implication in mineral physics. And our results have helped to understand the behavior of related compounds. Indeed, according to our results, both iron vanadate and chromium vanadate are more suitable than indium vanadate for photocatalytic water splitting, and indeed they are also less contaminant materials. So I think they should be tested in the future for this application. Just to conclude, I have many acknowledgements. First one of Pablo Botella, who was our PhD student. He finished the PhD and did many of the studies I presented today, and he moved to work to Saint Matt, which is a company working nearby us, and Alberto Bomiero from University of Lulea, who was the co-supervisor of Pablo, then Catalin Popescu and Alba Synchrotron for all the help on the experiment, all the members of the high pressure group in Valencia. I will not list them because we are many, and also the Polytechnical University of Valencia. Part of the acknowledgements go to Alka Garg and Achari from BARC in Mumbai in India, who also contribute to these studies and collaborate with us from the very beginning. And also Alfonso Muñoz, Plácida Rodríguez Hernández from Universidad de La Laguna in the Canary Island, and Sinue López Moreno from CONACYT Mexico, who were the three persons in charge of all the DFT simulations. And probably there are many others involved in the experiments and calculation who I forgot to mention today. And just again, I want to finish my funding sources, which is the Ministry of Science of Innovation and Universities of Spain and Generalitat Valenciana. And also thank you all of you, and I apologize by the technical problems at the beginning of the presentation. Thank you very much.
Thank you very much, Daniel. Very interesting presentation. I have quite a few questions for you, but I would like to give the chance to our participants here to ask any questions if they want to. So feel free. I don't see any questions in the chat box, but if anyone wants to just ask directly, just please go ahead. So I can't see anything at the moment, so I will just start myself. It was very interesting for me. I must be honest that I don't have much experience with high pressure measurements, but as you were talking, I thought with the Xray measurements, you could potentially reconstruct complete phase diagrams of these materials, right? If you measure also at different temperatures. Do you have any plans to do that, or?
Yes, this is something is done nowadays. It can be done. So you can combine high pressure and high temperature. This is more challenging, but it can be done without doubt, no problem. For these compounds, I think they will decompose at low temperatures. Low temperatures that will mean probably around 1000 K, they will decompose. So the experiment can be done with the resistive heating system. We didn't think on doing on these compounds. We have done it in many others. So, but yes, since for instance, in indium vanadate, there is a high pressure, high temperature phase, which is different from the high pressure phase we found at ambient conditions. Then yes, it could be interesting to determine the phase diagram and see if the boundary phases are positive or negative, and see if they can be validated by calculations using the Clausius-Clapeyron model. Yes, this can be done.
Very interesting. I'm also wondering whether you have tried to measure. I mean, I'm sure you've heard of them. Perovskites are very fashionable at the moment because they have a lot of applications in solar cell for solar cells construction, let's say, devices. So I was wondering whether you have characterized band gaps as a function of pressure of perovskite materials.
No. We have a very little work on perovskites, and we have never done it. To do a good characterization, we need a good single crystal. In addition, I mean, That's also, I mean, there are many other interesting problems I would like to study, but we have the resources we have and the manpower we have. So
of course.
it could be also interesting. And indeed, many of the studies we do come from collaboration from other groups, and we never had the chance to collaborate with a group working in a permanent way, collaborate with a group working on perovskite. So the synthesis of the samples is not something we do in the group. So we always need a collaborator synthesizing or growing the crystal for the studies. So we cannot do studies if someone else does not provide the samples.
I see. Well, I think in the interest of time, we're gonna stop there because we're already a bit past 4 and I don't want to take much more time from you. But I am really happy that you were with us, Daniel, and I found your work extremely interesting. So for all the people assisting, if you have any questions, please just contact us directly later on. And feel free to send us messages if you're interested or you want to propose some other speakers for our webinars. And feel free to also check our webpage because we have quite a few very interesting webinars coming up. So thank you again, Daniel, for your wonderful talk. And sorry also for the audience for the technical problems. You can never foresee those, but I think it went very well at the end.
Okay, so thank you, Elisa, for the invitation, for taking care of everything. And it was a pleasure to meet you.
Yeah, the same.
Okay, bye.
Bye-bye.